Excellent. Okay, so today is lecture 3 now. So we had some really interesting questions. So before we start today's lecture, where we'll talk more about algorithm building blocks, previously we've talked about data modeling, and before then we talked a little bit about the syllabus and a roadmap of where we're going to go. So I had some questions in terms of lab work and installing Java and the distinction between Java and Visual Studio Code. And so we should take a moment, I think, just before we start talking about algorithms and the building blocks of algorithms, we should take just a moment to talk about the technologies we're actually going to be touching and using to build out our software. So first and foremost, this class is going to use the Java programming language. And so the Java programming language was, and still is, it's one of the most popular languages that you can learn. It's the most popular enterprise level language you can learn. We brought in actually an adjunct professor who works in industry, and he's worked in 3 or 4 different positions, always in Java. There's a lot of Java related development, and when you go into the professional world, it's a very relevant language. And the reason why is because Java is designed in a way that scales up with code and with people. So there are languages that can be a little bit easier to initially learn, but they don't scale as well. So languages like Python and JavaScript, you'll learn over your tenure as a student, are great for smaller projects. But where Java is really going to shine, it's going to be hard to get this depiction over the course of this semester, is when you are working on an application that's hundreds of thousands of lines of code or millions of lines of code, and you have teams of 20 to hundreds of people all working on the same code base. That's one reason why Java is still so popular today, is because it really supports the ability to scale up a code base to be that large. So what does it take to run Java? Well, the Java language is essentially, any programming language is essentially packed as effectively like an application. So you can install the Java language onto your system. It usually exists in effectively 2 different flavors. You have what's called the JDK and the JRE. The JDK stands for the Java Developer Kit. That's what we use to take what we're going to learn how to code. So it's going to take our source code and it's going to compile that into what we call bytecode. So that becomes executable code, machine code that no longer is human readable. But by default, the machine can't read our human readable code. So there's always this translation process between taking what we can read and what the machine can execute. And so that's what we use the JDK for. And then you have the Java runtime environment. The Java runtime environment is super portable. Almost any computational machine, regardless of whatever it is, not just laptops or mobile smartphones, but also things like toasters and set-top boxes and refrigerators, and everything runs Java. So Java is portable because what Oracle does is they maintain what's called the JVM. That's the Java virtual machine. So unlike languages like C or C++, where your source code is compiled down into object code or code that actually executes on the actual hardware, Java code executes so it can run inside this virtual machine that is an application in and of itself on your computer. So your code only has to compile to the JVM and not the actual hardware, which makes it incredibly portable, right? So anything that has a JVM, your Java source code can compile to. So instead of having to be aware of all the different hardware restrictions, like you might have to on a C application, you can be agnostic of that and just program for the JVM. And that's also one reason why Java became so popular. It's not just the portability, the idea that you can write your code one place and it can execute no matter what the platform is, but also the fact that since it executes in a virtual space and not in your actual hardware, it was a safe way of being able to exist in this interconnected world where the internet was this burgeoning thing, Java grew up alongside the internet. And this idea of having a virtual machine that you can execute code, there was an awareness of the security implications of that, right? You don't want to just download some source code that you didn't author yourself off the internet and run it on your machine, because it could be highly destructive. It could destroy it could erase your hard drive, right? It could give some other user privileges to your machine. So to prevent having hardware level access whenever you ran any kind of application, that's what motivated this concept of a JVM. And still, that's one of the major ways that software runs today, is inside these virtual environments. JavaScript works the same way, but it's housed inside the browser, which is even a stronger walled garden. So then there's all sorts of tools that allow us to author our Java code. So when we're talking about Visual Studio Code or Sublime or IntelliJ, these are all what are called editors, right? Code editors, and some code editors will offer really some nice quality of life features like syntax highlighting that will go ahead and it'll display your keywords in a different color than the variable names, for instance. And so when you go to author your code, typically you're going to use a code editor to do that, which will make it much easier to kind of read your code base. But then when you're done authoring your code, you actually use Java or Java C. Java C is short for Java compile, to actually compile your code from a .java file, right? That's the human readable format, to a .class file, which is going to be the compiled version. And that compiled version can then be interpreted by the JVM and actually execute so that it can run on your system. So does that help clear up kind of how these different technologies interact with one another? Does anyone have questions related to that? Excellent. So if there's no questions related to that, let me see here. Let me make sure I'm logged into my system. What on earth? Then I want to start today's lecture, but I want to make sure I have access to my web terminal here. If not, that way we can use the same system that you have access to.
I think your audio is muted.
Have I been muted the entire time?
It only just got muted.
Perfect.
Like
okay.
after you exited the share screen.
Well, I think what happened, I won't use web terminal to demo because I can't share my screen. So let me set myself up locally really quick. So I'll have a new Finder window. Let's see, for new Finder, let's jump to desktop. Perfect. Inside of desktop, let's create a new folder that we'll call 2022 CSCI 1583. This will be the place that all of my demo code goes now. Let me go ahead and open up a new terminal at this folder. Okay, perfect. And so now I have a Bash terminal. Okay, let's clear this. Let's do ls, present current working directory. Perfect, that's what I want. Okay, and then let's do this. Let me make a file output. Okay, We will come back to that. And let's put this on this end and this end. Okay. So let's start with today's lecture. So algorithm building blocks. So previously what we spent a lot of time doing was discussing the role of data modeling and how what we strive to do whenever we start developing software, which we haven't started doing yet, is understand that we have to take our observations of a problem domain and map it from this concept model that is inside of our head, from a mental image, into some more rigid form of data. And we discussed how to do that in confines of recipes, for instance. So now that we understand that data models are part of this concept, the other part is an algorithm that makes use of our data models that actually steps us from a beginning point and leads us to some endpoint. So algorithms are not something that's just restricted to software. It's not something that's just restricted to computer science. You can build an algorithm in any domain. You as a human can follow an algorithm, right? It's just a sequence. It's just a step-by-step sequence of instructions, right? But we make use of algorithms computationally to be able to automate tasks. So in the same way that you can follow an algorithm, we can define an algorithm in a way that it can be handled by a non-intelligent system like a computer. Now, with that said, a well-designed algorithm doesn't have to have any awareness. It doesn't have to make any decisions beyond blindly and mindlessly executing an instruction. So one of the other difficult things, there's two difficult things that we're going to encounter when we first engage in computer science. The first is taking our observations and mapping them in the form of data. But the second will be being able to articulate an algorithm that's so well defined that there is no erroneous abstractions in it, that there's no decisions that have to be made by an outsider reader. And so you want to think of it this way. It's like, have you ever tried to explain a process to, say, for instance, a 5-year-old, how explicit you have to be, right? Well, a 5-year-old is infinitely more intelligent than a computer is, because a 5-year-old still has thought and consciousness and the ability to understand instructions. And actually, if you give a little bit of an abstraction, it can fill in the blanks. Computers can't do that. They do exactly what we tell them to do and nothing more. So that's an important, so if you think it's already challenging to explain a process to a 5-year-old, it's going to be that much more challenging to explain it to a computer. But once you do, if you can explain it to a computer, it's certainly reproducible by anything else. So it's definitely something, a skill set that's worth learning, and it's going to be a skill set that you'll have to master in order to design any kind of software. Okay, so let's take a look at our building blocks. So fundamentally, every algorithm inside of our computer system can be derived as one of 5 basic building blocks. So we'll talk very abstractly, very generally about what these building blocks are. So we have output operations, we have storage operations, we have input operations, we have processing operations, and we have control operations. So we build out our software. Each statement inside of our algorithm will manifest as one of these things. Sometimes we may have multiple of these operations in one line of code, in one statement. So we can sequence these basic operations together to build any algorithm inside of our software system. So let's start explaining what these types of operations are. So let's start with the output operations. We'll start with number 1. What is it? Well, the output operation is responsible for getting data out of our program. It says to the user, but just out of the program. It doesn't even have to be to the user. So let me put to the outside. So an example here that you've probably already seen inside of your lab is where we do like system.out.print, and then you put in a string like hello world, and then on the console, it probably displayed that. I'm going to explain a little bit more what's happening there in detail. But the role of all output operations is to take some piece of data that exists inside the app and send it outside of the app. So what does that end up meaning? Well, you want to think of your app as being kind of like a walled in garden or like a walled in little village, right? Where everything coexists together, but it's separate, it's isolated around from all the other processes that are executing inside of your OS, right? Like when we create our application, we are reserved computational space and memory just for our application, and nothing else is allowed to get into it or out of it without our allowing it, without us allowing that. So we essentially hold the gates to that kingdom when we define our application. We're the kings and queens of that domain. So what's really critical then is most applications just don't have everything internally to do what they need to do. Most of the time, it's very critical that we're able to get data into the application from the outside, from a place that is not predefined inside of our app. And at the same time, there are often times where we need to take something that we've processed within our application and export it out, send it out of the application. So we're going to look initially at getting data out of our application, and that's what the output operations are all about. Again, responsible for getting the data out of the program to the outside. So we want to think of our apps as being like walled in, where we have control within the app. And so we use a concept of streams to move data out of the app. And in fact, we're going to use the same concept to move data into the app, but we're not on that operation. And so when I say streams, conceptually, think of it like a river. So think of our application as if it were the city of New Orleans, surrounded by nothing but swampland, muck and mire, where everything is inside the small community. But we have a river where we can import things into the city or export things back out of, right? And so the concept that we use to be able to bring data in or take data out of our application uses the same concept of the way a river is used to bring goods and goods and materials into a city and export it back out via ship. So we can put things into the stream and then we can collect it from the stream, or we can put things in the stream and we send it back out to some other application. That if I'm upriver and I'm throwing stuff into the river, then on the other side, the other application can be plucking things out of that stream. Does the concept make sense? Okay, perfect. So Java has a built-in class named system that represents our computer system, that represents things that we want to have access to the underlying system that our app is running within. And so one of those things that system has are input streams and output streams. And so in order to do the output operation, we're going to have to take advantage of the system's output stream that's given to us, that's predefined for us. In fact, whenever we see something new, I'll try to go ahead and open up the API. If you're not familiar what an API is, it stands for a application programming interface. It's essentially the set of rules, it's a set of descriptors about every class and every method that's defined in Java we can read about inside of the documentation. So if you're going to become a successful developer, it becomes very important to be able to start reading the API documentation very early on. So let's see, we have system here, and we get a description of what the class is. The system class contains several useful class fields and methods. It cannot be instantiated, and it effectively gives us things like these input streams and these print streams. So that's what we're going to make use for. And then in the next class, you'll learn even more about how to use streams to be able to read from other sources besides the initial system.input stream. But we're going to really just use this for this semester until you get comfortable with these concepts. Okay, so there are three different types of print statements inside of system.out. We have print, we have println, and we have printf. Did you cover all of those in the lab by chance? Okay, so let's do some demos and so we can see how these all interact. So let me grab this code. Don't want to open IntelliJ. No, stop IntelliJ. Quit. Don't open. Okay. We want to open with, I'm going to use Visual Studio Code. Okay, let's see here. And we will paste this. Okay, so what do we have going here? Let me make this bigger. Although I'm sharing the screen, but can everyone see? Can everyone read that? Okay, so when we first go and make our code, the thing I want to highlight here is the output operation we're doing is line 4, but we can't do an output operation in isolation with Java. So let me explain some of the fundamental rules for building software in Java, just so I can build a basic demo for you, effectively a hello world. So this is the output operation. Everything else around it is what's needed just to have a Java application constructed. So I'll try to build this up in terms of like a kind of like a nested doll of sorts. So we create our algorithms here, right? So this is a part of my algorithm. This particular algorithm exists with just one output operation, where the entire point is to display a message to the outside to our terminal that's going to say hello world. Now, Java is an object-oriented language. It's heavily object-oriented, which means we can't do anything outside of the concept of objects. This class is going to teach objects in a late object approach, which means initially we're going to have a lot of like hand-wavy boilerplate things, but I'm going to try to explain to you like what's going on until we formally introduce the idea of objects. But what I will say is that there are multiple paradigms where we could develop code. We could do, say, for instance, procedural. We could do functional. We could do object-oriented. And so the approaches we have here, all of our statements, Java enforces on us, has to go inside of a method. And so in order for a Java application to actually execute, it has to have at least one method that is the main method. So when you launch the JVM and you send the JVM your Java file, if you want it to actually execute, the JVM tries to execute the main method as the launch point. So the main method is always the launch point for every application within Java, no matter how complex it is, whether it's a single line of code like this one, or whether it's millions of lines of code. It always starts with the same method name. So that method name is a special method that whenever you invoke Java from the command line and feed it a Java file, a compiled Java file, it's going to look for that. So we have to have it. So that's what I'm defining here. And so methods themselves have to be defined inside of classes, and classes are defined inside of packages. So effectively, all of what this has to do is ways of organizing our code so it's more manageable. So one of the things I mentioned that Java is so popular because it scales up really well. One reason why it scales up so well is it forces all developers to adhere towards a methodology that compartmentalizes your code so that it's easier to navigate and read through. So again, the chain or sequence of things would be, I have my instructions right here. So this is the algorithm I'm building. It has to exist within a method. We can't have any free floating statements. The statements go inside of methods and methods have to go inside of classes. So starting to build in reverse order, then the first thing I have to do whenever I build out any application is to define a class. And so you want to think of a class as a classification, right? It's a classifier of sorts. It's a thing of grouping a collection of related methods. Now, we're not learning about methods yet. We're just learning about these basic concepts that even allow us to implement a hello world. But later on, when we start learning about methods, you can understand that we can have multiple classes, and classes should be related. The things inside of a class should have relations where the methods are similar to one another. If the methods aren't similar to one another, then that means you should put it into different classes. Again, this is a little bit beyond where we're at now, but I'm kind of seeding the ground for the future when we actually get to those concepts. So we'll learn more about that in the lectures to come. But right now, just know we always have to have a class where we can then put our main method. So public is an access level type. We have a couple different types, but the two main type is something could be either public or private. If it's private, it's effectively like the same access types you can put on a file or on like a social media profile, right? Like if it's private, then the outside world doesn't have access to it. If it's private, only this class would have access to it. And if it's public, then anything has access to it. We need it to be public because we want to run our code from the command line. The command line's not part of this class. So the only way that we can give access to this main method to our command line where we're going to execute our code from is to label it as public. Does that much make sense as in terms of the public? So all these things you see here are keywords where when Java goes to parse this and compile it into machine code, or what we actually call bytecode, it has certain keywords that it parses for the purposes of Java itself. So for instance, when we start learning how to create variables, we can't use any of the keywords as our variable names. Those are restricted because they have special meaning inside of the Java programming language. So public is one of those such keywords. We know that it's a keyword because it highlights blue inside of my syntax editor. So the nice thing about these code editors is that it lets me know different parts of the language as I'm authoring it. So then the next thing is a class. So this is allowing me to define a namespace where I'm going to be able to start inserting a collection of methods. And then the name of my namespace, the name of my class, the name of this place where we're going to put all of these methods has to be the same name that your Java file is called. So I created this Java file called output-demo.java. Well, it's going to, my class name has to be the same as the Java file name. So there has to be that one-to-one correspondence there. And I'll show you what happens when that doesn't match up, just so you can see in case you encounter that error. Okay, so then once we're inside of the class scope, so then we create these curly brackets. The curly brackets in Java, and this is really common in many other programming languages as well, allows us to define what's called a scope. So this allows us to open up this class definition that we've just created. And then we also have another curly brace that closes the class definition. So when I start coding, let me cut this out. When I start creating my class, I always open and close my curly brace at the same time. It's super important because if you're missing a curly brace, your code won't compile because it doesn't. If you forget a closing brace, then you're not closing the scope of a class or a method or some part of your code. And so that prevents your Java file from being able to parse and understand where your sequence of directions are supposed to stop at. So it's super important that whenever you open a code block, you also close the code block. And we're going to use these curly braces, not just in defining our class scope, but when we go and put a method inside of our class. So inside of our classes, we have methods. And so the first method we're going to learn how to author is going to be the main method. For some time, at least for the first batch of weeks, we're just going to use the main method, and then we're going to graduate out and learn how to create our own unique methods inside of our class. But we have to at least have this one. So the main method also has to be public because it gets invoked from the outside. from not inside this class, but from our terminal when we go and execute our application. Static is the key word that doesn't necessarily hold a lot of sense until we have instances of objects, but just understand that static means that it's a property of the class itself, where we don't have to use the class as a blueprint to construct an instance from it, that we can just call the method from the class definition in and of itself. So I'm going to show you what that means, and I'll stress this when we get to the ability to contrast it against something else. But just understand for now, we'll always use the static keyword when we define our methods so that we can invoke them from within the class. The void means that this method doesn't return back anything. So methods can take inputs and methods can take output that can be shared across our application itself. So just like I said, our app as a whole is kind of like this walled community that is isolated from all the other processes that occur in the computer system. Well, each method is its own little walled house where everything that happens inside of it is protected from the other methods that exist. So we have the ability to feed data into a method or to get data back out of the method, but a method has to declare whether it's giving back data. And so if it doesn't give back data, then it has a return type of void. So that's what that void means. It doesn't have a return type. Later on, when we learn how to use methods, or when we start defining our own methods, we'll see some methods do have a return type where it can give back some data, and then we can use that data inside the method we're at. Every method has to have a name. So since there's an expectation that a main method exists, we have to call the main method name. So there's another caveat here based off of the notational directions that Oracle put forth, and before it was Oracle, it was Sun. We always name our class names with an uppercase letter. Always, always by convention, use uppercases for your class names. For your method names, they should always be lowercase. And then we have a set of parentheses here after the main method where we can pass in the data we might want to go ahead and supply to it. Here, this is a label. This could be anything. It's convention to call this args, short for arguments that you feed to the main method, but I could have labeled it X or argx or V or anything else, right? This part doesn't matter. This part does matter. This is the type of data that we'd expect to have supplied into this method. And so here, a string is text data. We're going to talk more about that in this lecture. And when you have the brackets around it, then it just means that it can be more than one piece of text data. And again, we'll see more about arrays. It's a construct that's called an array, still way before our time, but I just want to give labels to identify the parts you're seeing, and then we're going to slowly make sense of it as we go on. You can do that, but it is so here there was the statement that we can put brackets here after the variable name. That is legal, but I would not advise it because it's not clear. It's not clear when reading it, the type of data. So this is the square brackets act as a kind of mutator on the data type. So when we get to storage operations and we start talking about how we can start mapping different forms of data in our application, if we apply square brackets on the tail end of our data declaration, then what it conveys is that this piece of data can have more than one value. But it's easier to see when you contrast it, when you attach it to the data type as opposed to the variable name. It's fine for now. Just know conventionally, even though it's legal to do it in the alternate way, conventionally you want to group it with the data type and not the variable name. But it's fine for now. I'm giving you, one of my roles is to give you convention expertise as well for the notational distinctions, so that when you go and read code, or if you're going to produce code that other developers are going to read, it's more in line with what the Java developers typically author. Okay. this is really all of that stuff. And again, after we declare all of like what the access level is, whether this method has membership to the class, or whether it's what's going to be called an instance method. We're going to ignore instance methods for now, whether it has a return type or whether it has a set of parameters and a name, then we have to give it a code block. We have to assign an implementation to it. So just like with class, we're going to open up a pair of curly braces and also close a pair of curly braces. And then our actual operations, our algorithm operations can go in between those curly braces of a method. So this is where we finally get to do our output operation. Okay, so notice I use two-dimensional formatting as well that allows me to see where my code blocks are defined at. So where my scopes are. So we call anything in between code blocks a scope. That's a jargony term, I guess we use. So here, the scope of my class starts here and it ends here. So to visually allow me to see that very easily, I'm going to indent everything that's in between those two curly braces, right? So now just looking at my source code, I can say, hey, this main method is defined within this class. Because notice that's much more readable than something like that, right? This is technically valid. I can execute that, but it becomes less readable for us. In fact, Java doesn't require us to use any kind of formatting rules. I could make all this code one line and it would compile and execute, but it would become very difficult for us to read. Like, in fact, this would all be, right? This is all legal here, right? Like that's completely legal. I can compile that, that would run, but that becomes very difficult to be able to parse and debug. So we avoid that. We use this formatting scheme as opposed to that. Okay, is there any questions regarding this yet in terms of just like the boilerplate code before we even talk about the system.out.print?
You were saying that in the section output demo that you always capitalize the first word. Is that correct?
So let me see. So whenever we define a class, we always capitalize the first word or the first letter in our class name. So that's the case. Whenever we define or give a label to a method, we always use a lowercase name. So methods use lowercase names and classes use uppercase names. Now, if your name is more than one word, we use what's called camel notation. And camel notation, based off of what Oracle and before Oracle Sun, is the preferred way of taking two words and meshing them together for the purposes of creating a class name. So let's talk about some rules for our class names and method names, and this will extend out to variable names as well. They can't start with a number, right? They have to start with a letter. You can't have spaces between them. You can't use any special symbol that's used that are kind of reserved for parsing. So you can't use like curly brackets, you can't use apostrophes, you can't use quotation marks, because we're going to learn that those are all used for other operations inside of the Java programming language. So you can use underscores, but we don't use underscores for the most part in Java, because what's preferenced is using underscores is what's called snake case. You use underscores if you're authoring Python, you use camel case if you're authoring Java. Technically, yes, it's legal to use snake case, but if you read the notational guidelines that Oracle puts forth, they advocate against it and instead going for camel case. The reason why we want to be familiar with these notational rules is that it sets up an expectation with other developers. So when other people go to try to use your code, and if you use different notational rules, it becomes more challenging for them to intuitively guess how your code works or to remember how your code base works. So it's much better if everyone's on the same set of using the same kind of styles, so that you have this built-in expectation. It's like if you say, for instance, create a argumentative essay, you probably have to follow what MLA rules, right? Well, that's the same for when we alter our code in a professional sense. Like if you're developing code just for yourself, it doesn't matter. But the idea is that you want to go into the workplace, you want to be have a profession, you want to have an occupation of software developer. So it's important now to start considering the rules by which we even do things like variable naming, or how we go ahead and declare our methods and our classes and things like that.
When you were running straight into you put LN after print.
Yes, and in fact, we're going to talk about that. So like I said before, we have 3 different print statements that we have access to in order to learn how to take data from inside of our application and send it to the outside. Now, when I say the outside, what print does is it sends the application out to the terminal, and it sends the application out to the terminal in the form of text. So effectively, what we're really thinking of with the print statement when we're saying send the data out is we're going to send it out so that it could be printed. Now, clearly, as you evolve to be a more fluent Java developer, you might want to export your data in more complete ways than just as a text representation. You might want to export it as data types that can then be loaded into another application. So you might want to export the actual data that can then be used, or you might want to export files, or you might want to export graphics, or all these other kinds of things that applications can do. But since we're going to start with the basics, we're going to just, at least for this class, restrict ourselves to just exporting text. Now, later on, when we look at the homeworks, we're going to see that Princeton has created a really cool class called the standard draw class that will also allow us to essentially display graphics. And so we'll do that with the homework, but inside the lectures in the lab, we'll reserve ourselves just to having text representation as our output. If that, but there are 3 ways we can send text out, and we're going to look at that. Print ln is one of those. I want to start with print because that's the default. That's the initial one. So here, like I said, we have a representation of our underlying system that's part of the standard library that Java supplies to us. So again, the way that Java accumulates a collection of classes is what's called a package. A package you could think of as a directory, as a folder that has a lot of class files. So the default package that we get is the java.lang package. And part of the java.lang package is the system class. I can actually verify that by going to the API. And if I go to the system here, we can see that system is defined. Here, you can see the class system, which is predefined for us. And the dot operator means that this thing is inside this other thing. So if you've ever seen like a file path, is everyone familiar with a file path on a computer system? Like you can have directories or folders, like say, for instance, the C drive. Inside the C drive, you have like a desktop folder or documents folder. And inside of the documents folder, you might have a like homework folder. And inside the homework folder, you might have like a text file that's called like myfile.txt. Everyone's like for instance, here, right? I have this file here, 2022 CSCI1583, and inside here's this Java file, right? So typically what's the delimiter we use to show that a file is inside of a folder and a folder is inside of another folder? What symbol do we use on the OS? Yeah, we use a slash, right? Like it's C/, right? And then desktop / homework / myfile.txt. The slashes represent a delimiter. It represents that the thing on the right-hand side is within or nested within the thing on the left-hand side. Everyone's comfortable with that concept, right? Well, that's exactly what the dots mean inside of Java. So when I see here, everyone sees what I'm highlighting here. Let me zoom this up here. Inside the API, showing me system is inside. The dot represents system as this class that's inside this package lang. So that's the default package that we get all of our, no matter what code we write, by default, we always get the system.lang package available to us without having to explicitly import it. We can get other packages into our software system by importing them, but by default, we always have access to anything that's in java.lang. And since system is a member of java.lang, we can call on it without having to import it. Later on, when we learn how to use the scanner object to be able to start getting input into our application, we'll actually have to import that because that's part of the java.util package, which isn't one of the default packages that's automatically imported for us. We have to explicitly import that. Okay, so system is a class that's defined for us as part of the standard library. Like I said, system has input streams and output streams. That's that abstraction that allows us to get things into our software or to get it back out. So we want to access the output stream, and the output stream, one of the methods it has, one of the behaviors that an output stream allows us to do is to send things to it to get printed to the console. So I'm going to use the print method. So when we invoke a method, it has these parentheses attached to it. So in order to print something, I actually have to send something to get printed. And so I'm going to send text. So the way that I declare text, or what I'll call a string inside of Java, is to put it in between quotation marks. If it's not between quotation marks, then Java thinks that that's going to be a variable name or a reserved memory address. So here we'll have the quotations to open our string and the quotation to close our string. And we're going to say, hello world. And then what we want to do is we want to print a new line character after that. So I'm going to use this escape sequence and then an N to highlight that that's a new line. And I'll show you what this is. We'll play around with it some so you get a feel for this. Let me, okay, so let's clear my, so the first thing I'm going to do here is once I have my hello world application, I'm going to make sure it's saved. Now that it's saved, I'm going to call Java C. That's short for Java compile. Can everyone see that? Is that big enough for everyone to read on the terminal? Okay, so Java C, and then I'm going to use the name of the Java file that I want to compile, the name of the Java file that has the main method. So it's going to be called outputdemo.java. And so when I run that, that's going to run through the JDK. What it does is it's going to parse this human readable source code, and it's going to compile it into this .class file. You see, I now have a .class file. I didn't have that before. If I try to bring that class file into my editor, you're going to see it's no longer human readable. So open anyway, saying, hey, this file is it's a binary file. So here, and that's what it looks like now. So now it's something that the machine can execute, but we can't read, whereas this is something we can read, but the machine can't. So that's why we have that compilation step. That's the translator between human and computer linguistics. And then once we have this .class file, we can then call the JRE, the Java runtime environment, using Java, and then I can give it a Java executable, Java class file, a bytecode that I wanted to run. So here's going to be output demo. And so when I execute that in my terminal, we'll see now what prints to the terminal, what gets sent to the output stream that my terminal then gets and then renders is going to be hello world. Now, let me show you a couple of things here. If I don't put that new line character, I can do this just fine. What do you think will happen if I don't put the new line character with just a print statement? Let's see, let's run this. So actually, let me clear my terminal. So I'm going to remove that and we're going to run that. And notice it prints hello world, but since I didn't embed a new line character, the terminal is just going to start rendering the next pieces of data out from there. So now I get kind of this really muddled, dirty hello world, and then I have my user prompt immediately thereafter. So again, what's happening here is if we put an escape sequence, the escape sequence lets the terminal know, hey, this isn't something we want to print as part of the string. This is a formatting instruction that we want the terminal to know, create a new line. So if I do escape N, that's going to make a new line character. So for instance, if I put escape, so /N, and then if I run that, so let me do that in front of hello too as well. So what you'll see here is now hello's on one line and world is on another line. And notice, since I technically have a space there, world is actually spaced out as well. There's a space there. So does everyone see how that output works? And in fact, N isn't just the only thing. I could put a T there too if I wanted to. That is an escape sequence that would embed a tab there. So here, if I run that, notice here, I have a tab in between those. And in fact, there's all sorts of escape codes we can put into our string that the terminal will then render in interesting and novel ways. So it's not just the ability to add tabs in or add new lines in, but we can also add emojis in. We could add a color of the text or color of the background. So we can use ANSI escape codes to actually change the color of our text or change the background color. We can use the Unicode escape sequences to actually do Unicode symbols or emojis. So you have a lot of cool things you can do inside of a string when we do these print outs. Okay, is there any questions in terms of just the basic print statement here? Then the next thing I want to do is inside of lab, you said you used ln, right? Print ln. So what print ln stands for is print line. The ln stands for line. And so what ln does is it automatically appends a new line character to whatever data you're supplying it. So instead of us manually putting that escape n character, that new line character, it'll actually do that. So here, if I do print ln, and if I compile that and then run that, then we could say I have hello world all on, let me see here. Okay, perfect. And here you'll see that it embeds that new line character for me. And then finally, I have, now I could still also embed new line characters inside of the string. So if I do this, or if I put a new line character after, let's do that. Let's put the new line character after hello world, but with print ln, what that's going to do is it's going to produce a double new lines. So here you see I have my new line, but then I also have an empty line. Okay, so the last print that I want to show you is going to be the printf. So printf stands for formatted print. So this allows us to embed data into a formatted string. So a formatted string might be something like this, hello, and then I'll do something like %s, and then anything that has a % is effectively a placeholder value where I then have to add a comma after my formatted string, and then I need to add a substitute for what that placeholder is going to be. So here I'm going to put world, and actually let me put the new line character here. So what's going to happen with the printf statement, and these are my favorite, these are what I'll be using all throughout the semester, is going to be, let me clear this, let me compile my code, and let me run the code. And what you're going to see as output is I'm going to get my hello world. And what's happening here is this is what's going to get displayed. But for each %s I have here, or each placeholder value, %s is a string placeholder value, I can then add something here that will then replace the %s. So to put that in perspective, let me put another one. And then I'll put, say, for instance, by here. And we will combine that. And you'll see here now my string says hello world by. Excellent. So those are really, and we can have more placeholders. Like if I use, say, for instance, D, that could be a number. So instead of by, I could put like the number 10. See, and then that's going to print out 10 for me. If I put F, I could do a fractional number, so like 3.4. Just like so. So I can have different placeholders embedded in my formatted string, depending on what type of data it is, whether it's text data, whether it's numerical data, and that numerical data is an integer or a fractional number. Excellent. So does anyone have any questions about the output operations? Excellent. Okay, so we looked at print, we looked at print ln, we looked at print f. So the next operation that's going to build our basic building blocks for algorithm design is going to be storage operations. So output operations allows us to send data out. We can't do much with just output operations, right? So any algorithm that we're going to design is probably going to be a combination of all 5 of those operations we talked about. Storage operations are super critical, though. They're responsible for saving data so that we can use it later on. So by default, whenever we have data on a particular line of code, it doesn't exist after that line of code is done executing, unless we store it into memory. So storage operations allows us to take a piece of data from one line of code and reuse it in future lines of code. So it's an immensely important operation to be able to do, which is to be able to take data and store it and mutate it over time if we want to, as our application continues to run. So now this is going to be the big thing. If we're going to store data, when we initially declare or reserve memory to store our data, we have to let the JVM know, we have to let the computer know the type of data we want to store into memory. And the reason why is that different types of data consume different amounts of memory. So when we declare a variable, it has to know how much memory to allocate for the data we want to store there. So usually when we create a storage operation, it's at least 2 pieces of information we have to supply the system. It's the type of data that we want to store, and then we give it an alias, a label, a name that we can call that piece of data later on so we can recall it. And it's just like anything else. Like if you want to be able to name, if you want to be able to reference something, you have to give it a name. That's true in the real world. That's true in software, right? The moment we try to describe anything, the first thing we do is label. And that's exactly how software development works as well. So fundamentally, there are 3 types of data. So we're talking about building data models, and we represented building data models using recipes before. And so we talked about how data can be quantitative or qualitative, right? The quantitative is when we can ascribe like a numerical value to data, but not everything can be defined as a numerical value. And those that can't is qualitative data. So numerical data represents things that are either integers or floats. So the count of people in this room could be represented as a quantitative piece of data, as numerical data. Text, like your name, can't be quantified. So that would have to be a qualitative data that could be representative of text. So that's another type of data that we can represent inside of our applications. And then you have a concept that isn't text and it's not numbers. It's the idea of something being either yes or no, or true or false. It's a Boolean value. And of course, Boolean sounds like a weird term for that data type. It's named after George Boole, someone who had great influence in the math of Boolean logic. So if you're wondering where that term came from, it's like most things in math and science named after somebody. So now we have like an eclectic kind of jargony term, which doesn't understand that whenever we say a Boolean data type, we're talking about something that's true or false. We're talking about text-based data, we're going to call that strings in Java. And when we're talking about numerical data, we're actually going to distinguish between whether the number is an integer or the number is a fractional number or floating point number, right? Those are 2 different concepts. Even mathematically, those are 2 different concepts. Those belong to 2 different sets. So we'll have, so whenever we want to create a space in memory to hold any one of these data, we understand what the data type are. There's a set of primitive data types that are built into Java what makes a data type primitive in Java is, first of all, it begins with a lowercase letter. It's a reserved keyword, but second of all, it's every value that can be mapped to that data set is defined within inside of that data type. So for instance, all the possible values of Boolean is true and false, right? It only has two values that Java understands. For integers, there's a max int and a min int. So it's not an infinite number of integers. And because of that, there's different encodings. They have like shorts, they have ints, and they have longs. And longs can have a larger amount of values than a standard int, and short would have lesser values. They use more bits to encode or less bits to encode. And then fractional numbers can be represented either as float or doubles. It's usually preference to use double over float because it's double the precision. And so floating point numbers are always approximations. You can never truly do, and this is true conceptually, not just, it's not a computational limitation. This is true on radix points numbers or floating point numbers generally, is that you can't really check them for equality. So when you go and do things like calculus, typically what you'll try to do is you'll find what your allowed error rate is, what amount of flexibility or delta value you can have to consider something to be approximately equal to. And again, you can always, like the classic trope that's usually you in a math class, and you'll see this probably in discrete math class if you haven't already seen it, is the very real fact that the integer value of 1 is equal to the radix point value of 0.999999 repeating. Like those necessarily have to be equal for the convergence of our radix math, our floating point math, and our integer math to operate across one another. Otherwise, all sorts of operations like division would break and not produce any true answer. Okay, that was a little bit of a detour, but let's take a look. I have a couple minutes to take a look at our sort operations. So they're responsible for saving data for later use. There's 3 types of sort operations, just like there was 3 types of print statements. We have the ability to just declare a variable. So variable declarations will reserve a space in memory for some future data value of a particular data type and give it a label and give it a reference name, but it doesn't assign a value to it at that time. It just reserves it. Then we have assignments. Assignments can store a value in a piece of memory that has a reference name, that has a label that's already been defined. And then if we want to declare a space of memory and assign it a value all at the same time, that's called an initialization. So we can declare variables, we can assign values into variables, or we can initialize a variable where we're doing both a declaration and an assignment. So let's take a look at some sample code there. And what I would like to do here is actually just go ahead and execute this. So I'm going to put this inside of my, so I will, so the first thing I'm going to do, I'm going to slowly evolve the code so it's easier to read as I walk through this. So the first thing I'm going to do whenever I go and construct any code, oh, let me not get rid of my other source code file. Let me make a new one. So first, let me make, what was this called? I want to say it was output and storage demo.java. So the first thing I'm going to do is I'm going to make a new Java file here. So I have an output and storage Java file. It's output and storage because I'm going to have print out in addition to my storage. There we go. Okay, so let me go back and actually grab the source code since I started cutting it apart. Okay, so now that I have this Java file, I'm going to create a class definition and then a code block that's associated with it that uses the same name as the file name. So output and storage demo. And then inside of my class, I can start defining methods So again, the class is just a container for methods. So here, we're only going to use the main method for now. So I'll create a main method. So this is an example of an initialization. So here on the left-hand side, I am declaring a data type of int. So it's going to be non-fractional numerical data. I'm going to provide a reference name that I can use within this application that will be called integer number, and I'm going to assign it a value. So this is an initialization. If I did this, let me turn the initialization into declaration and assignment just so that you can see. So that would be just a declaration, and that would just be an assignment. So when it's all in one line, it's initialization. Then once I do that, I can print it out. I can make another. I can then do my assignment here, print that out. I can do here on line 11, you see, I could do a double data type that lets me do fractional numbers. I can do a data type of Boolean that allows me to assign a value that's either true or false. Notice true or false are all lowercase. I can do an individual character, which is a single quotation, or which is a primitive data type. It's a car. Or I can do a string, which is a reference data type, which uses double quotation. So I want to ask one question, and then I'll let everyone go today. What do you think the difference is between the car data type and the string data type? That's right. And so that's going to motivate this one last insight I want you to have. Notice for every other data type we saw, which is the integer, which is the double, which is the Boolean, and the car, they're all lowercase. I stated earlier, that means it's a primitive data type. That means what it means to be a primitive data type is every single value within it is predefined inside of Java. But string has a capital letter. It's an uppercase letter, which means it's a reference data type. Why do you think that's a reference data type and not a primitive data type? Why can't strings be like ints or doubles or Booleans or cars? And well, like I said before, numbers have a predefined ordering, right? Like you have 0, 1 comes after 0, 2 comes after 1, 3 comes after 2. And I said that in integers, it doesn't have an infinite number of integers. It has, let's see what the scope really quick is of integers, so that just so you can see integer, min, max, Java. So integers can be anything from this value to this value. Anything larger than that, and you got to declare it as a long. But with a string, there's no ordering with text, right? I can have the letter A as a string, then I have the letter as AA as a string, and then I can have the letter AAA as a string. When am I ever going to get to AB? I might never get to AB. So there's no way for me to pre-code every permutation of text into the Java JVM. And so therefore it customizes it as you declare it. That's what it means to be a reference data type. It's not pre-built values in the system. It has to store it in memory. And we dissociate reference data types from primitive data types by giving them an uppercase letter. Okay, that's what I want to, we'll talk more about that next time on Thursday. Remind me about that. But that is a little bit of an insight between what's going to delineate between our primitives and our references, which will be an important concept as we move forward.